So there is a controversy if you know the rearrangement. That is, I think you are familiar with the stability of carbocation. If a question something like that, which is more stable? Which is more stable? Okay. And you are given that CH3, CH2, CH2, CH2 plus, okay, CH3, CH2, CH plus CH3. Which is more stable? If a question something like this, which is more stable? Which one is more stable? Okay, fine. Secondary is more stable than primary. But there is a doubt. If this primary can rearrange, right? If it rearranged, what happens? It becomes the very same. If it rearranged, what happens? CH3, CH2, CH plus, CH3. Now, why this is more stable? There may be a doubt in your mind, something like that. Okay. Once you know the rearrangement. Oh, this can form the very same carbocation. Okay. Now both are having same. There may be a doubt. Okay. Now both may have same stability. No. Stability only compared on the basis of initial structure. Initial, not on the basis of rearranged structure. It's only applicable if there is a carbon intermediate in your reaction. Okay. In order to compare the stability, you simply consider the initial structure. It is secondary. So there is 2 plus I donation. 2 plus I donation. You know that alkyl carboketones are stabilized by inductive effect and hyperconjugation. What are the chance for hyperconjugation? How much? 5. Okay. Here only donation from one direction, since it is a primary, and 2 alpha hydrogen. Okay. So this is more stable than this one. There is no doubt. Even this can rearrange from the very same structure. Okay. So in order to compare the stability, you simply consider the given structure. Okay. Is it okay? Okay. Fine. Consider the given structure, not their rearranged structure. Okay. Rearrangement only for what? Only for which is only applicable in a reaction where intermediate is a carbocation. Okay. Not for comparing stability. Okay. Keep it in your mind. Ready? Okay. So once you know the rearrangement, there will be a doubt. Something like this. Okay. Both have same structure, then which is stable. Okay. So the rearrangement is actually for the second beta elimination, and that is the second beta elimination is what? Dehydration. Dehydration. Okay. Dehydration of what? Alcohol. Okay. There is no doubt this mechanism is E1. Usually the acidic dehydration is E1 mechanism. E1, you know, first of all, the forms a, like your SN1. Forms a carbocation, where rearrangement is possible. Okay. So dehydrate alcohol. Both the reagents for the dehydration of alcohol is either concentrated sulfuric acid in presence of heat, or concentrated phosphoric acid in presence of heat, or it may be Al2O3 heat, P2O5 heat. These all are dehydrating for alcohol. Okay, this is simply shown like this: H plus in heat. Okay, where the mechanism is E1. Listen here. Listen. You should know the mechanism, otherwise the answer will be wrong. If I have butane 2, butane 1 nol, listen here, butane 1 nol, which are acidic dehydration, represented like this, H plus in heat, H plus medium in heat. Now the mechanism is E1. Okay. If someone do this without mechanism, just like your dehydrohalogenation, what will be the product? Someone do this without considering the mechanism, just like your dehydrohalogenation, you know that this is even mechanism. Okay. If someone do this is without considering the mechanism, the product will be but-1-ene. Agreed. This is a elimination just like your dehydrohalogenation. Ready? Where even mechanism follows. This is an example for says the elimination. Okay? But the very same molecule, if then first he have to remove the OH minus. He have to remove the OH minus so that there forms carbocation. Is it okay? Then with the structure of carbocation, CH3, CH2, CH2, CH2 plus. This is a carbocation. So first of all, you simply leave the OH minus, then you obtain a carbocation intermediate. Okay? Check whether rearrangement possible or not. Here, possible. So carbocation intermediate, rearrangement possible. Okay? Then you should rearrange that one by means of then CH3, CH2, CH plus. So make the carbocation formed into a maximum stable form by means of rearrangement. Okay? Once you obtain the maximum rearranged version or rearranged carbocation, you simply leave hydrogen from alpha carbon of carbocation and make a bond. Okay, once you obtain a rearranged carbocation, you simply leave H plus from the nearest carbon, nearest to the positive charged carbon and make a bond. Is it okay? So there are two chances, right? If I leave H plus from, if H plus even mechanism, then your product will be CH3, CH2, CH double bond, CH2. Or if it is from here, CH3, CH double bond, CH3. Which one is the major? This is phase of elimination. Okay, so this is a major. Okay, if somebody don't know the mechanism, his product will be but it is not major. If somebody knows the mechanism, the answer will be butane. This is the actual answer. Okay, so dehydration of alcohol should be in a even mechanism. And you know something about the rearrangement, then only your answer will be okay. Okay, wait, I'll give you one more example. Listen here. If I have a molecule like this, is an alcohol. Which one? Acidic dehydration. Like acidic dehydration. What do you have to do? Remove the OH and make the carbocation. Check whether rearrangement possible or not. Ready? You know now how to rearrange a carbocation. And it become a this is the most stable form. Okay, then consider the, once it become a tertiary, consider the alpha and leave hydrogen so that you obtain a bond. So this alpha hydrogen and this alpha hydrogen are identical, right? So there are only two possibilities. From here and the exactly same possibility. So the chances one will be right? And according to size of rule, this will be the major. Is it okay? Okay. So the dehydration should be through the mechanism. The mechanism is even. For even, you have to know how to rearrange a carbocation. That's why the previous section rearrangement. Okay. Fine. with this molecule. Okay, first show the enzymes of elimination, E1 mechanism. Can from so it's okay. Remove the OH minus and bring the carbocation into more stable form. Then leave hydrogen from the alpha position and make a bond. Then compare the stability of the formed alkene. Then that will be the major one. Okay. Wait, this is the rate determining step, okay? This is the RDS. And this mechanism which is given in your NCERT of alcohols, dehydration of alcohol, the mechanism is given in your alcohols, okay? So you have to know the mechanism. It may be discussed in your chapter alcohol, okay? This means this reaction depends on what? The stability of initial, this reaction depends on the stability of, not the rearranged one, initial formed carbocation. If the initial formed carbocation is a tertiary, the reaction will be faster. Okay, always the stability that depends on the initial form, not based on the rearranged form. Rearrangement is only for, is applied in the case of a reaction to design the product. Okay, to check the possible products. And I'll give you one more examples. The ideas are same. Okay, the ideas are same. If you are given with an alcohol, you simply remove the OH and you obtain a carbocation. The carbocations may be in any style. Okay, then check whether rearrangement possible or not. If so, you simply rearrange it. Consider the alpha position. Okay, then based on the very same size of rule, you can predict the major. Okay. Okay, question may be something like this based on the nomenclature. Major product when 2,3,3-dimethyl butane 2-ol on reaction with the concentrated sulfuric acid for 43 Kelvin. So which means that this is an acidic dehydration of your alcohol. Okay, first you design the structure, then you consider the reaction. Hydrocarbon is a basic chapter, okay. If you know the basic idea of hydrocarbon, then the other reaction chapters will be more easy. It's a basic chapter, including free radical, carbocation, all mechanisms. Okay, in your haloalkane there are only carbocation. Got the answer. What is the IUPAC name of your formed alkene? IUPAC name of form. In your choice, there may be the names. Okay. 2,3 dimethyl butyl 2E. Okay, there is a methyl shift, right? What about the reactant? CH3, C, CH3, CH3, CHOH, CH3. This is butane 2-ol. Agreed. Which one? Acidic dehydration. Remove the OH minus so that you obtain a carbocation like this. Agreed. Chance for rearrangement based on the alpha portion of carbocation. There is no benefit if the positive charge in this alpha, right? But if the positive charge in this alpha, it becomes tertiary, so that there is a chance for there are only methyl, so chance for methyl shift. Agreed. So CH3, see CH3 here is a plus CH, CH3, CH3. Okay. Followed by this is the most stable one, right? Then you leave the hydrogen from the alpha portion, alpha, alpha. alpha, but these two alphas are identical. So the chance of CH2 double bond agreed. First chance. Right? I have 12 alpha hydrogen. Okay. So this will be the major product. Agreed. Alpha, 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 alpha. 12 alpha hydrogens are there. This is the major product according to size of row. Okay. And the name is 2,3-dimethyl U2E. Okay. So question may be in this pattern also, which of the following is more easily dehydrogenated? Sorry. More easily undergoes, which of the following alcohol more easily undergoes dehydration? For that, you have to compare the stability of initial formed carbocation or the stability of formed alkene. Okay. The alcohol which easily dehydrated means that depends on the stability of initial formed cation or the stability of formed alkene. Stability of formed alkene. Okay. So write a point. Rate of dehydration. Rate of dehydration. Rate of dehydration depends. Rate of dehydration depends either the stability of C plus formed, either the stability of C plus formed, either the stability of C plus means what? Either the stability of formed carbocation, C plus formed, or the stability of formed alkene, or the stability of alkene, formed alkene. Okay, ready? So if I have a question like this, which are the following, write a question, which are the following most easily dehydrated? What about the first one? The first set. The dehydration easiness will be like this. Okay, because here the formed carbocation will be here the formed carbocation is stirred butyl, right? Agreed. Formed carbocation is a tertiary, stable. Here it is secondary, not much stable as this. Okay, work here. Primary. Okay, so this is the order which is on the basis of stability of carbocation formed. What about the next? Can be on the basis of stability of carbocation or on the basis of stability of alkene. First one, what about the carbocation formed? That's an allylic carbocation. Agreed. Allylic. The second one, a simple secondary carbocation. Secondary alkyl carbocation. Third one is a vinyl carbocation. Vinyl carbocations are relatively unstable. Why? In ring, the vinyl carbocations is much unstable because a double bonded carbocation have an hybridization of sp. Sp means the carbon should arrange in a linear shape. Okay, but it is not possible in ring. In your ring, there is the molecule, the carbon will be either in a planar fashion or something like this, never in a linear pattern. Okay, in ring, any carbon which can't exist as linear. Okay, so this is highly unstable. So here generate a sp ring, not possible in ring. The sp hybridization in ring, it is not feasible. Okay, in an open chain it is possible. Ready? This carbocation has stability, even though this is sp, but it is in open, acyclic. It can in an open chain it can exist as sp, but ring never possible. Okay. What about this? What about this one? Both are primary carbocation, right? And the difference in stability due to the presence of NO2. Okay, you know NO2 is an electron withdrawing group. Electron withdrawing group this NO2 withdraws electron, so that the intensity of the electron deficiency increases, stability decreases. I think you know that. Electron withdrawing group destabilizes carbocation. This is already an electron deficient species. Okay. Moreover, some kind of electron density withdrawn by a group means its deficiency increases, its stability decreases. Okay. Then what about the next? This is also electron withdrawing group. Okay. Then which one is more stable? Inductive effect is an effect which depends on distance. Okay. Any kind of inductive effect, psi or minus I, that is inversely distance. As distance increases, the corresponding inductive effect decreases. Okay. So where the plus I is maximum? In the first one or second one? In the second one, the distance increases. The minus I is minimum. Agreed. So minus I minimum, where here the distance is plus, so minus I maximum. Minus I maximum means here the stability minimum. For the stability and minus I effect, stability of carbocation that is inversely proportional to minus I effect. Okay, so which structure have greater minus I effect means this one, which means this have lesser stability. So the stability of carbocation follows in this order, therefore the order of dehydrogenation also in this order. Okay. What about the next? is to be beta hydroxy ketone, beta hydroxy, and this is gamma hydroxy ketone. Which have greater heat of dehydration capacity means beta hydroxy. Even this is a minus I group. Ketone is a minus I group. You know the order of minus I. Ketone is a minus I group. But the formed unsaturation may be in conjugation here. This is a minus I group, agreed. This is a minus I group. Okay, so here will be the carbocation. What about the carbocation? Tell me. Okay, here. Okay. This is a minus I group. Minus I group in a close distance. Okay, so our expectation is stability higher here and lower here, but the hydrogenation is reversed because the formed, what about the formed alkene in this molecule? This one. This is in a conjugation. This CC double bond is in a conjugation with this one. Why? Double bond, single bond, double bond. What about the this is non-conjugated. Okay, so the higher heat dehydration will be in this molecule. That depends on the stability of formed alkene. Okay, either that depends on the stability of carbocation or depends on the stability of formed alkene. If something like a conjugation is there, then that will be the reaction more tend to form that conjugation, which means the greater higher dehydration will be here. Okay, so I think you are okay with the difference. In beta hydroxy ketone, the formed alkene will be conjugated with the keto group, even though that is a minus I group. This is in conjugation. Resonance have greater priority. This is in conjugation. But what about this one? This is in a non-conjugated pattern. Okay, so the more stable for this formed alkene. So greater dehydrogenation for this one. Okay, so no need to consider what? No need to consider the stability of intermediate. Okay, so that's a special point. Beta hydroxy ketones have greater tendency for dehydration because the formed alkene will be in conjugation with the formed CC double bond will be in conjugation with the CO bond. You know that there is a resonance. Okay, where this bond jumps to here, this to here, and form a plus bond O minus like this. Okay, there is a resonance where the negative charge is in an oxygen. That's extra-stable. Where this in that sense, there's a resonance actually is extra-stable because this bond is in conjugation. Okay, so that you have to keep in mind. Beta hydroxy ketones have a ready tendency to dehydrogenate compared to the other hydroxy ketone because the dehydrogenation of beta hydroxy ketone leads to the formation of conjugated CC double bond with the keto group. Okay, so enough. That's all about dehydration. Moving to the last method of preparation of alkene, but that's also important. Dehalogenation. Dehalogenation of vicinal dihalide. Dehalogenation of vicinal dihalide. This is the method number 4. Okay. Dehalogenation of vicinal dihalide. Dehalogenation of vicinal dihalide. halide. Okay. The reagents may be zinc in dry ether, or internal Woods reaction. If vicinal dihalide means what? You know the difference between vicinal and geminal. Vicinal means the two same function groups on a alpha beta position. This is said to be vicinal dihalide, where if the two same function group on a same carbon, then it is geminal dihalide. If halogens from a vicinal dihalide eliminated, what happens? They forms a bond and become alkene. Okay. If sodium in dry ether is used, this halogen leave to form a bond. Internal Woods reaction. Okay. So for the dehalogenation means removal of what? Removal of X2. It can be done by zinc in dry ether or our sodium in dry ether, or it may be by sodium iodide in dry acetone. These all are the reagents. The most important reagent is zinc in dry ether. The common reagent is zinc in dry ether. Okay. So first of all, you have to know the difference between vicinal and geminal. Okay. Vicinal and geminal. Ready? The reaction is very easy based on structural explanation, but we have to explain this reaction on base of stereo. Okay. So dehalogenation of vicinal dihalide. The reaction is very easy. Listen, I have a vicinal dihalide something like this: RCH, CH, R dash, where here is an halogen, here is also an halogen. Which one treatment with the zinc in dry ether? What happens? Zinc brings the two halogen so that there forms a bond. So become R, CH double bond, CH R dash. What do you obtain? Alkene. So this is very easy on the base of structural product or structural reaction. Base of explanation on the base of structure is very easy. Listen, I'll give you example. If this is a compound, okay, and your vicinal molecules are usually named as alkylene. Alkylene, where the geminals have alkylidene. Okay, so this is propylene. This is vicinal, right? So propylene chloride or propylene dichloride. If these two chlorines are in this carbon, then it is propylidene dichloride. See the difference, okay? Alkylene, alkylidene, okay? So if zinc in dry ether used, what happens? And it become propene. Okay, if I have an example, something like this. The forms a bond. Okay, this is easy, but it's stereo-wise explanation. You have to know that, okay? So first of all, show this. So simply, this is a reaction, but there is a chance for stereo-wise explanation. And that's important for the next reactions. So this is the last method of preparation of alkene. write a point. Dehalogenation using zinc in dry ether. Dehalogenation using zinc in dry ether. Dehalogenation using zinc in dry ether is trans elimination. Dehalogenation using zinc in dry ether is trans elimination. That's important. From that word itself, you have to define the stereochemistry of this reaction. Okay? Listen. Trans elimination. So this process is a trans elimination. Okay, listen. I have a reactant. Listen carefully. I have a reactant and have a process to form a product. If we know the configuration of reactant and process, if we know the configuration of reactant and the process, here the dehalogenation using zinc in dry ether, the configuration of the process trans. If you know the configuration of reactant, then you can predict the configuration of product. Okay, it will be okay once I explain the whole. Okay, that is, if your reactant have a configuration of cis and the process have a configuration of cis, then your product will be cis. Okay, if your reactant have a configuration of trans and your process is a trans, then your product will be a cis. If your reactant have a configuration of process is a, then the product is a trans. If the reactant configuration, okay, so don't try to study cis plus cis, trans plus trans like that. If the reactant undergoes the process of same configuration, if both are same, then you obtain cis. If both are same, cis. Both are cis, cis. Both are trans, cis. If there is any change, trans. Okay, try to be in that pattern. Okay. First you copy this, then I apply the concept here. Okay. If both are same, cis. If any change, trans. Make it silent, okay. So this is okay. Ready. Keep it in mind. Both are same, then cis. Listen. Then how to apply that concept in a reaction? That is important. Okay. Ready? Listen here. I have a vicinal dihalide. Let it be vicinal dibromide. This is a vicinal dibromide with a stereo. Okay, you know that any two corner in a cyclic ring can show geometrical isomerism. So this is a geometrical pattern where the two bromines, one is in a front plane, another is in a back plane, and these are trans. So this molecule is nothing but this is trans what? The name of this molecule 1,2 dibromocyclohexane. So this is a trans 1,2 dibromocyclohexane. So it is okay. This is a vicinal dihalide, right? So this one reaction with the zinc in dry ether, what happens? What happens? Bromines are leaved and form a bond, okay, bond here, right? And if you are adding zinc in dried. Zinc in. And you should know that this process elimination using zinc in driver is trans elimination. This process, that is the point. Elimination using zinc in driver is trans elimination. So we have to apply this concept. Okay. This molecule is trans. Okay. This molecule is fine. And the process, and you obtain. So you simply remove these two bromine and make a bond, and that bond should be in a cis pattern. Okay, so this is cis cyclohexene. No problem, there is no trans. There is no trans. There is no trans if the carbon is from 3 to 7. Only cis. In cyclohexene, with respect to the bond, the configuration only cis if the carbon is from 3 to 7. Anyway, the product is cis. Okay, wait. Why it is cis? The product is A and the molecule is A. So it should be cis. Fine. Two bromines are in a same plane. Either use or solid weight or by dash. Both indicates that the two bromines either in a front or in a back. So this is the cis 1,2-dibromo cyclohexane. Both are same. Okay. Which on treatment with the zinc in? The process, the initial molecule is, you have to form trans. Oh, but the reaction is not feasible. Why? Means there is no trans-cyclohexene. Trans-cyclohexene is unstable, so this reaction not takes place. Okay. Ready? Okay. Show that. Doubt? Fine. Camera. Okay. There is no existence of trans cyclohexene. That's why the reaction is not feasible. Okay. Listen carefully. Listen. This is a saturated molecule. Agreed? Your reactant is a saturated one. Your reactant is a saturated molecule and your product is a unsaturated. With respect to unsaturation, it is very easy cis and trans, right? With respect to unsaturation, it is very easy to define cis and trans. Agreed? You know cis and trans with respect to unsaturation. It is clear that you have to define as cis and trans in the reactant and in the process and in the product. Process is always trans if it is zinc in triether. Agreed? And the product is an alkene, double bond, unsaturation. It is very easy to define cis and trans if it is an unsaturation. But it is much difficult to define cis and trans if it is a saturated one. No problem if it is a cyclic one. There is a problem if it is an open chain. How can you define cis and trans in an open chain? Open chain means single bonded. If it is a single bonded cyclic, no problem. Geometrical isomerism observed, we can easily define cis and trans. If it is a single bonded open chain molecule, how can you define cis and trans? That's the question. If you are able to define cis and trans in a single saturated open chain molecule, then only you can predict the product. Okay, so listen carefully. If I have a molecule like this, what? CH3, CH, a bromine, CH3. This is a single bonded molecule. Okay. You should define, or you have to know, or you have to define whether this is a cis or trans. That's the problem. Okay. For that, this is a chiral carbon. Agreed. This also chiral carbon. Agreed. So this is a symmetric molecule. Hence, it have three stereo arrangement. Let me show the stereo arrangements. Let me show the stereo arrangement in Fischer projection. Okay. CH3. The final CH3 here. And here we have H and Br, right? H and Br. H, Br. Br, H. Or H, Br on both sides, same side. Okay, this is some kind of stereo arrangement. Ready? Or the next possibility, it may be alternate, right? It may be in a, here the two bromines are in the same side, right? Same side. If two same groups are on a same side of a Fischer projection, then such arrangement is said to be erythro arrangement. If two same groups are exist in the same side of a Fischer projection, then it is said to be erythro. Or your erythro is simply treated as a cis. Okay? Why? It is in the same side. Is it okay? Okay. Generally, the molecule is known as erythro. This form is known as erythro. If anything, if two same groups are on a same side of a Fischer projection, then it is said to be erythro. And your erythro is simply considered as a cis. Okay. And this is actually meso 2,3-dibromo butane. Mesoform. I think you are familiar with the mesoform. Mesoform means a form with a plane of symmetry. There is a plane of symmetry. Okay. This is simply 2,3-dibromo butane. Agreed. But this form is said to be meso. Why means? Due to internal compensation, its optical activity will be lost. This is said to be having a plane of symmetry in this plane. The upper and lower are same. So this molecule is said to be meso. Okay? Fine. This is meso if and only if this CH3 and this CH3 are same. Listen. Is this one is defined as meso. Listen. Every erythroform is meso. Is every erythroform is meso? No, this is not meso. Why? There is no plane of symmetry. This is simply an erythroform. Okay. Is it okay? Is there any symmetry? No. This is ethyl and the top is, they are entirely different. This is simply a erythroform. Okay. In your carbohydrate, there is erythros, triose. Erythros, 4-carbon aldose, erythros and triose, and based on 2 OH on the same side, erythros, OH on opposite side, triose, like that. Okay, fine. So this is a general idea. Then what about here? BR, HCS3. One more chance is there, it's mirror image. One more chance is there, it's mirror image. But here the mirror image is same. I think you know about that. HBr. Okay. So these are the optically active. This molecule have 3 optical isomer. 2 optically active and 1 optically inactive. Ready? If this is dextro, then this will be levo, or this is levo, that will be, we can't predict that. Okay, it is only on the base of rotation of plane polarized light. It's an experimental fact. Okay, if this is dextro, since this is a perfect mirror image, this can be predicted as a levo, or vice versa. So this forms is generally these 2 forms. This form is known as this form something like a trans. So this we can treat it as a trans. Actually, this form is known as trio form. Trio. Erythro means same side. Trio means. So the molecule can be named as plus or minus. Plus or minus. These 2 are together known as plus or minus 2,3-dibromo butane. Okay. So listen, you have to define the stereo of your reactant, and you know the stereo of your product. Then only you can define the stereo. Sorry, you have to define the product, stereo of reactant and stereo process. Then only you can define the stereo of product. Okay, it is easy to define the stereo of a double bond. Okay, but it is little difficult to define the stereo of a single bond. No problem if it is a cyclic ring, because already it can show geometrical isomerism. This is not on the basis of geometrical isomerism. This is simply an assumption. Okay, based on the stereo arrangement. Okay, is this molecule can show geometrical isomerism? No. This is the different stereo arrangement. On the basis of the arrangement of, we can simply consider it as a cis-like, trans-like. Is it okay? Ready? So this is cis treated as, erythroform is treated as cis, always thrioform treated as. If I have, listen, if I have, what happens if zinc triether is treated with this? 2 bromines bond. Agreed? 2 bromines are left to form a bond, and you obtain but2e. Okay, but this molecule is a, and our process is a, so you have to form trans, which means the formed alkene after this elimination. If this bromines are gone, there will be a bond. Okay, and the molecule should be trans. Okay, trans. So debromination of meso 2,3-dibromobutane forms trans between. Debromination of meso 2,3-dibromobutane forms. Know how to design that product. Meso means have symmetry, which means erythroform. So something like a cis, and zinc in triether is a trans. So you have to obtain trans. Okay, what about combination of plus or minus 2,3-dibromobutane? What do you obtain? This molecule is a, and your process, and you obtain, means you obtain cis butene. Okay, is it okay? Fine. Wait, I'll give you one more example. If something like this. Okay, in order to define the stereo arrangement of a single bonded saturated open chain molecule, they have to mention the, or you have to give, you are given with the Fisher arrangement or stereo arrangement. Otherwise, you can't predict that whether it is a cis-like form or trans-like form. Okay, you should given with the stereo arrangement, then only you can predict that. Okay, but in the case of cyclic molecule, they can say that is cis 1,3 dibromo. Okay, or else they can say meso or plus or minus. But in the case of molecule with the symmetry only, otherwise they have to give the structure, then only you can answer the question. Okay, this is a frequently asking question. Ready? Debromination of meso 2,3 dibromobutane forms, mainly forms choice A, cis-butene, trans-butene, like that. Okay, then you have to choose trans-butene. If and only you know the idea about this stereo reaction, stereochemistry. Listen, if the molecule is this one, and I am treating it with the zinc rather, this is a mesoform? No. Is there any symmetry? No. This is simply an erythroform. So they should give the structure, then only you can identify whether it is an erythro or trio. So this erythroform is treated as, and your process, and you obtain, so you obtain trans what? Trans what? CH3, CH double bond, CH, CH2, CH3, transpentene, pentuene. Okay, not pentuene. Agreed. Trans will be like this. This is what? Trans. Cis trans, fine. Transpentuene. Okay. Fine. You can copy that. Question may be like this. Debromination of meso 2,3 dibromobutane dominantly gives or plus or minus 2,3-dibromobutane, like that, okay? Otherwise, they will give the structure. So you have to know meso means erythro in this case. Plus or minus means trio. Otherwise, they will mention the there will be any idea for having a conclusion that whether it is erythro or trio, either the structure, or they say that erythro. Okay, then only you can design the product. Ready? If the question is on the base of stereo, on the base of structure, it is very easy. You simply remove the chlorine and halogen and make a bond. Okay. Okay, normal beta elimination we know. Okay, beta elimination using alcoholic KOH we know that it may be E1 or E2 or E1 CB. Okay, but in some question they mentioned it as E2. Okay, and you have to know the E2 mechanism. Then you know what is E2 mechanism? Not this reaction, the reaction which is already discussed. Beta elimination, dehydrohalogenation of alkyl halide. You know the mechanism E2. The removed halogen and hydrogen should be anti-periplanar. Then only the reaction taking place in E2 mechanism. If they specified it as E2, then you should design the product on the basis of E2 mechanism only. So what about here? What are the chances? Listen carefully. What are the chances? This is alpha, here is beta, here is beta. What about the beta hydrogen in this carbon? There are two beta hydrogen. If one is in If one is in words, the other one in? Agreed. Here also a hydrogen. Okay. Which is the size of position? Which beta is size of? Look this molecule in a structural pattern. Cl. Which one is the size of position? This one. Agreed? And here there is a hydrogen, right? Which is in dash. Okay. So what about the E2 elimination? It should be anti-periplanar. The chlorine is in a front plane. Where here we have an hydrogen in back plane. So E2 possible. Here the chlorine is in the front plane, where hydrogen is in the back plane. E2 possible. Here also possible. So better to eliminate from here, because E2 mechanism also follows size of rule. Ready. So what about the product? Is it okay? What about here? Is there any change? Yeah, there is a change. The chlorine is in chlorine changed its configuration. So what about the hydrogen here? Dash. So this elimination not possible, because it should be anti-periplanar elimination. Okay, then you obtain the hydrogen from only top. Is it okay? This is only possible. Sorry. Okay. This is the only product. It's not major, only product. Okay, why? This is E2 elimination. Should be anti-periplanar, where this hydrogen is in the same plane with the chlorine. So there is no E2. But this hydrogen is in the opposite plane with the chlorine. So there is a chance for E2. Even you obtain less substituted alkene. Okay, but here we have two chances. So the better one is Secha. Okay, what about here? So you obtain a trans butane. Okay. Ready? This is the chlorine. Okay. There we have two hydrogens. One is in the same plane, another one is in the opposing plane. So this will be the style of elimination, because this is E2 and you obtain. The hydrogens are existing opposing position, so you obtain. I'm sorry, this is trans. Okay, trans. Here will be one hydrogen, here will be the another hydrogen. This one and this one. Okay. You can't predict whether it is E1 or E2. If they mentioned it as E2 or E1, then you can do the question like that. Okay. Wait. First of all, you copy the question separately. Otherwise it will be more confusing. Then you show this one. You copy the question separately. Then you write once again, then show this. Otherwise it will be more confusing. Okay. Chlorine, methyl. This is the first question, and it follows E2. They said that it follows E2. In the second case, where the methyl is in the words, but chlorine changes to dash. E2. You copy the question first, okay? Then make the answer separate. elimination, hydrogen and halogen should be anti-periplanar, means opposing plane. That is the point that you have to remember. Okay. Okay. Chemical property of alkene. Chemical property. Okay. Chemical property, most important property is addition, actually electrophilic addition. Okay, where the controversy is in unsymmetric addition. The controversy is in unsymmetric addition. Symmetric addition is very easy. You simply cleave the bond and add the same reagent on both sides. There is no controversy. The problem is in unsymmetric addition. So there are three different symmetric additions. Okay, the very same reverse reaction is here. That means alkene on halogenation. Alkene on halogenation. The bond cleaved, two halogens are added to form vicinal dihalide. What about the previous reaction? This is previous reaction. We have vicinal dihalide. Dehalogenation forms alkene. Now the reverse. Alkene, halogenation forms Vicinal dihalide. Okay. Ready. So vicinal dihalide on dehalogenation forms alkene. That is a trans elimination. Now alkene on halogenation forms vicinal dihalide. That's a trans addition. So there also we can arrange stereo-based problems. Exactly the reverse of this one. Not this. Reverse of dehalogenation. Okay, so there are two types of addition mainly, symmetric and unsymmetric addition. First of all, symmetric addition. Symmetric addition. Chemical property. First of all, symmetric addition. Okay. Symmetric addition. So in the second example, only less substituted alkene forms, okay, since the mechanism is E2, because antiperiplanar hydrogen is in the less substituted position. Okay. Symmetric addition A, halogenation. Halogenation. Halogenation means addition of halogen. The halogen, either it may be, usually it may be chlorine or bromine. If it is bromine, then bromine in CCl4. Okay. If it is chlorine, normal Cl2. Chlorine in sunlight may switch on the mechanism. Okay. So either chlorine or bromine in CCl4 is a reagent. Okay. Combination are not usually observed. Okay. Reaction is very easy. You have alkene on halogenation. What happens? This is symmetric addition. Cleave the bond and insert to halogen there. Okay. So what do you obtain? R, CH, R. Here is a halogen. You obtain vicinal dihalide. Okay. So this is a trans, it's not elimination, this is addition. So trans addition. Okay, structural examples are very easy. If I have butene, listen, have butene, I'm chlorinated it. What happened? Here is a chlorine, here also chlorine. Okay, if I have propene, if brominated in presence of CCl4, what happens? Here is a bromine, here also agreed. But if it is in presence of heat, that's allylic substitution. Allylic, it is already discussed in the case of alkene. Allylic substitution, bromine in heat. This is allylic position. This is substitution, but this is addition. Mechanisms are entirely different. Okay. Wait. Listen. I have, this is cis cyclohexane, which on bromination. And the bromination is? So your product will be trans. Trans means this bond cleaved, two halogens will be here. It should transfer. How become a trans? Dash and bridge. Exactly the reverse is discussed. Okay. What about the next possibility? Trans. There is no trans cyclohexane. Okay. There is no. So the next possibility is not here. Ready? Okay. If I have, listen. If I have, what is this one? What is this one? Cis-butyl, which is brominated in CCl4. This is trans, and the process and your product is single bonded saturated trans, which means plus or minus. It is something like this, right? the reverse. Okay, this is trans with respect to unsaturation. On the reaction, your form will be saturated. So this is an open saturated trans, which means your 3O form. Okay, the reverse is discussed, right? So this yes. Okay, what is the name of this compound? Plus or minus 2,3 dibromobutane. Okay, the reverse is discussed. You can check it whether it is the reverse. Check it. Okay, so normal reaction is okay, but stereowise is okay because you know the idea. Okay, but the concept is reverse. So you should not by heart it. It may confusions. You have to know the concept. Otherwise, it will be mistaken. That's all.
CO2 is trans-assisted. CO2 is trans-assisted.
This is not based on stereo. This is simply on the basis of structural. Okay. Ready? Here, no stereo considered. Simply the structure like this is treated as a structural example. Okay. Okay. Here it is a stereo. This is simply based on structural idea. Okay. This is simple butene. Okay. Not mean trans butene. Ready? Okay. What about this configuration? Whether it is trans or cis? Whether it is erythro or trio. Is this structure is erythro or trio? That's erythro. You don't know. Converting this to fish. Okay, because you don't know how to convert a dashboard. This is a dashboard arrangement. Okay, you don't know how to convert a dashboard arrangement to fish. That's a problem. Okay. Okay, so take this as a structural example. In 3D form, if something like this will be in a erythro fissure. Okay, because there is an exact idea for the conversion of a 3D form to fissure. Even more than one chiral centers are there. Okay. So treat it as a structural example. Okay. So bromination of transbutene. If a question is something like that, you have to think that transbutene, bromination, your product is cis. Cis means saturated cis. Saturated cis means meso, erythroform, meso. Okay. This is the bromination of cis-butene, cis-bromination trans, so saturated trans, which means trioform. If that is 2,3-dibromobutane, that trioform is otherwise known as mesoform. Sorry, plus or minus form. Okay. Exactly the reverse. Correct reverse reaction is discussed, right? Okay. So in symmetric addition, this kind of stereochemistries are usually used. The next example is addition of Bayes reagent. Addition of Bayes reagent. Addition of Bayes reagent. You know, Bayes reagent is dilute KMnO4. Okay, exactly it is called alkaline dilute KMnO4. Okay. So addition of Bayes reagent. Bayes reagent. In bracket hydroxylation. Addition of Bayes reagent in bracket hydroxylation. So this process, not halogenation, hydroxylation. What do you mean by hydroxyl group? So hydroxylation means 2 OH are added. With respect to the unsaturation, 2 OH are added. Okay. So hydroxylation. This is an example for hydroxylation. Right, what is Bayes reagent? Bayes reagent is called dilute alkaline KMnO4. Okay. Why it is mentioned in this pattern means alkene have a reaction with the hot KMnO4. That is an entirely different reaction. Okay. But this reaction, if it is a cold KMnO4. So you have to know that alkene can react with the hot KMnO4 oxidation reaction. Will be discussed after this one. Okay. So alkene can react with the cold alkaline KMnO4 through symmetric addition pattern, say hydroxylation. It can also react with the hot alkaline KMnO4. That's why simply the dilute KMnO4 is expanded to cold alkaline KMnO4. In the case of alkene, we simply mentioned it as dilute KMnO4 because there is no other possibility. Okay, here the Bayes reagent is well defined as cold alkaline dilute KMnO4. This is actually Bayes reagent, and this is hydroxylation. Hydroxylation means what? Addition of 2 OH with respect to unsaturation. Listen. So we have an alkene. Okay. So when on treatment with the dilute KMnO4 without heat, there is heat. KMnO4 heat, the reaction is entirely different. This is cold. Cold means there is no heat. Okay. So you simply cleave the bond and make 2 OH where alkene is oxidized. Alkene is if anything is oxidized with KMnO4, then the color of KMnO4 will be decolorized, right? Okay. So this can be used as an identification of test for unsaturation. I think you are familiar with that. Test for unsaturation. Because the color of KMnO4 will be decolorized, which indicates the presence of the unsaturation point. So this bond, and you obtain what? You obtain vicinal diol. It's not vicinal dihalide. Vicinal diol. Okay, geminal diol become aldehyde. Okay. Moreover, this process is a syn addition. What? What do you mean by syn? Cis. Earlier the process trans. This process syn. So this have a stereo. This reaction also have a stereo. Listen. If I have cyclohexene, what cyclohexene? Cis-cyclohexene. Which on treatment with the dilute KMnO4. The process syn. Syn means cis. Syn is an alternate name for cis. Okay. So cis is what you obtain? Cis means the OH in a same plane, either dash or wedge. Okay, here also you can define the stereo. The very same concept, cis plus cis forms cis. So just you have to know the stereo of the process here. You know this or how this is said to be cis. Mechanism is a different way. Wait. I'll give you another example. So you are given with the cis-butene, which on dilute KMnO4. What happens? This addition is cis. You obtain cis, saturated cis, open cis, litho form. Okay. Meso 2,3 diode, meso butane 2,3 diode, butane 2,3 diode, butane 2,3 diode. And you have to know the IUPAC state. 1, 2, 3, 4, butane 2,3 diode. Mesoform. This is a mesoform, right? Yeah. If you have trans-butene, what happens? Which on reaction of the way? That is cis. You obtain trans configuration. Okay. So you should be able to define the configuration of that. Okay. Ready. Copy the examples. Show the general one and mark it as in addition or cis addition. You can show the examples. Okay, normal examples are easy. Simply cleave the bond and structural examples are easy. You simply cleave the bond and make OH. Okay. Stereo examples you have to think. Molecule is meso butane 2,3. This molecule cis cyclo 1,2 diol. Okay. Usually the number of OHs are just front of ol, not like halogen. Halogens are haloalkene, whereas alcohols are alkanol. There is a change in name. Okay. Okay, so write that point. Alkene can decolorize. Alkene can decolorize base reagent, KMnO4. Okay, since the alkene undergoes oxidation, where KMnO4 will be reduced. Okay, the general point is already discussed. Anything which is oxidized in presence of KMnO4, color of KMnO4 will be discharged. So here alkene can oxidize. Okay, one more symmetric addition is there, then we can have a break. That's hydrogenation. Okay, hydrocarbon is a lengthy one. Okay, hydrocarbon aldehydes, both are lengthy. Others are relatively not much length. Okay, but you have to know the complete basic idea of hydrocarbon. Then only the other chapter will be okay. And moreover, you should be you should have a well idea in organic basic. Okay, then only the whole organic will go. Even if it is in online or offline, whatever it may be, you should have a clear idea about basic organic. Okay. Hydrogenation. One more symmetric addition is the hydrogenation. We already discussed hydrogenation of alkene. You obtain alkane. Hydrogenation using hydrogen bar, palladium, hydrogen bar, nickel. Okay. But this topic is for discussing the heat of hydrogenation. Okay. We already discussed the nature of reaction. Hydrogenation, we are given with what? Alkene, right? We are given with the alkene. So alkene on hydrogenation forms alkane. Okay, you already know the reagents. Okay, hydrogen bar, palladium, charcoal, hydrogen bar, platinum, hydrogen bar, nickel, like that. Okay, so what happens? And this is an example of a symmetric syn addition. Okay, this is already discussed, but a new term, that is heat of, just like your heat of combustion, there is a new term, heat of hydrogenation. Okay, for defining or for saying something about this one, the topic is again, okay, heat of hydrogenation will be negative. Heat of hydrogenation means if you are with an unsaturation which is hydrogenated, so that the forms a saturated one and they release some kind of energy which is said to be heat of hydrogenation. And a specified amount of energy released once unsaturation is hydrogenated. Okay, or simply if you are defining when 1 mole of an alkene hydrogenated, they release a specified amount of energy called heat of hydrogenation. And there may be questions to compare the to arrange the molecules in heat of hydrogenation. For that you have to know the stability of alkene. I think it may be discussed in your basic organic, and that is on the basis of hyperconjugated structure of stability of alkene. Okay, so you may ask to arrange the following alkane on the basis of stability or on the basis of heat of hydrogenation. Okay, so the idea is heat of hydrogenation is inversely proportional to stability. Okay, heat of hydrogenation is inversely proportional to stability. That's the point. So if you are asked to find, or if you are asked to arrange a following alkane in heat of hydrogenation, you simply arrange it is in the reverse order of stability. So for that you have to know the order of stability. Okay, then only you can arrange it in a reverse order. Fine. Okay, wait. This is a decreasing order of stability. Okay, I'll give you a necessary explanation. Listen, based on hyperconjugated structure. What about the alpha? Alpha. These are the unsaturated carbon. Alpha. For alpha carbon, I need alpha hydrogen. 3, 3, 3, 3. 12 alpha hydrogen. 12 alpha hydrogen is the maximum number of alpha hydrogen with respect to an unsaturation. Fine. What about here? If there is a ethyl substitution like this, so this be the alpha, 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 alpha. It reduces it to 11. So the maximum is 12. It is clear that this is more stable than this one. Yeah. Stability which is proportional to number of hyperconjugative structure, which is proportional to number of alpha. Ready. So this have more alpha hydrogen than this one, so this is more stable. Okay, second. 2, 3, 3, 2. 10 alpha hydrogen. So this is more stable, okay? Is it okay? Next. What about the next? Alpha, alpha, alpha. I'm sorry. 8 okay. 6 alpha. So this is up to this much. Okay. Alpha, alpha. 6 alpha. But this is more stable than this one. Okay, I'll give you explanation. Alpha, alpha. 6 alpha. The trans is more stable than cis. So here is the controversy, right? There is a separate explanation. Okay, the general sequence of an explanation of decreasing alpha hydrogen. Okay, what is this one? What about here? Alpha 3. No. So from left to right, what happens? Stability decreases. If you are asked to arrange in stability, you can consider this. Or stability decreases means heat of hydrogenation. Okay. So you need explanation for this one, right? Okay. Methyl propene, isobutene. Next is transbutene, right? Transbutene. The next is cisbutene. Listen. Both are same, okay? Ready? All have same alpha hydrogen. Then why this is more stable than this one than this one? That's the explanation. This is cis, right? Trans. This is where two bulky methyl groups are in the same plane in the case of cis. Okay. These two CH3s are in the same plane. Where these two bulky groups are in opposing plane. So since the two bulky groups are in same plane, there is a steric repulsion, crowding effect, which destabilizes cis form compared to trans. Is that okay? Fine. So trans is more stable than this one. What about this one? These two have same hyperconjugation. Agreed? These two have same hyperconjugation, but the hyperconjugated structures are different. Let me consider the hyperconjugated structure of first one. Okay, listen. You know the it's become H plus, where this sigma CH bond conjugated to here and the bond conjugated to here. So the corresponding hyperconjugated structure is, here is a double bond, will be a negative charge. Agreed. And here will be a H plus. Now bond resonance. I think you are familiar with the hyperconjugation. Okay. So this is the hyperconjugated structure of the first one. What about the second one? These two have same kind of hyperconjugation. Tell me the hyperconjugation. Let this have CH2H. These two have same kind of hyperconjugation, only the stereo arrangement is different. Okay, but here the structural arrangement is entirely different. Two CH3s are in same carbon, but here the two CH3s are in opposing carbon. Okay, so hyperconjugation of this one is equivalent to this one. So let me have the structure. This H become H plus, bond to here, this to here. What happened? CH2. I'm sorry. CH2 double bond, CH, here is a H plus, single bond, CH3 minus. Okay. Hyperconjugation of an alkene leads to the formation of carbanion. What? Hyperconjugation of an alkene leads to the formation of carbanion. Here the carbanion is a primary carbanion, where here the carbanion is a, which carbanion is more stable? Primary. That's why this is more stable. Its hyperconjugated structure have little stability, since the formed intermediate is, since the formed carbanion is more stable. Okay, so both can show same number of hyperconjugation, say 6, but the hyperconjugated structure have different stability. But this one have greater stability, since the formed carbanion is a primary, but that one have comparatively less stability because the formed carbanion is a secondary. Okay, no need of showing the structure, you simply know the explanation. Okay, why this is more stable? Means the hyperconjugated structure is more stable. That's enough. Okay. Why this is second stable means there is no repulsion. Enough. That explanation is enough. Ready. Fine. Okay. So minimum you can write that. Okay. Due to the stability of formed hyperconjugated structure, or due to the less repulsion. No need of showing the whole. Okay, that's up to you. You can show anything. So this is your note.